Okay, so welcome everyone. Thank you for joining this Local Talks event. It's our third event of the year. Our previous ones were in January and in June. No, was it January and June? June and April. Yeah, my name is Randy Kangizi. I'm a graduate architect at Localworks, which is the entity behind Local Talks, and we'll be hosting this session today. So for anyone who's not aware, Local Talks is a series of events around green design, and we aim to have 4 every year. And generally, it's our aim just to create an open forum for the exchange of ideas around this topic. Previous Local Talk sessions are always recorded, and these are available to watch on our YouTube channel. We've covered a range of different topics, and you are all welcome to watch if you have not watched some of them, if you have not before, or rewatch them whenever you like. Just to let everyone know, this event is being recorded, and we will begin with presentations from 2 speakers who have joined us today. These are Allan Semakula and David Wituszynski. The 2 of them will be speaking on the topic of green water solutions, and our subtitle to this is Alternative Rainwater and Wastewater Technologies in Uganda. Allan will be focused more on wastewater and David on rainwater. So I'm just going to give you a very short introduction to the 2 of them, a little bit more about their biography, who they are. And then I will hand over to Allan first, and following that, David will speak. After their presentations, there'll be a Q&A session where everyone is welcome to ask questions that you have to the speakers. And during the session, you can also put questions in the chat that we can discuss later. Yeah, so Allan is a founding director of Equator Sun, which is one of the building consultancy firms that is under the roof of Localworks. He is a qualified architect with a degree in architecture from Makerere University. At Localworks, he is the head of building services. David Wituszynski is a member of the research and development team at Engineering Ministries International-Uganda. His work mainly focuses on water technologies and on data collection and processing. He holds a PhD from the Ohio State University, where he managed both ecological and stormwater sampling programs. So that's a short summary about the 2 of them. And I think I've said everything as far as the introduction goes. I will hand over to Allan first, and then we'll hear from David.
Thank you, Randy. Share my screen. Like Randy introduced me, we are presenting green solutions to waste management, and I am going to again reintroduce Localworks. Localworks is a multidisciplinary design and build collaborative, and its pillars are research, design, build, and share. So I could say today we are at the sharing phase. We started the presentation that I have chosen to share with you. So 8 years ago, we had a client, this is Cotton Foundation, who presented us with a challenge, I will not say a problem, of designing for 500 children. This is an outreach school. Chalangea was one of many schools, and we are still partners to this day. So what we started doing is research and find out what solutions were available, what solutions were working. And on the first page, we look at what the problems were. That was lack of sustainable human waste management solutions, because we realized out there that the most common solution is pit latrines, and we all know what the problems with pit latrines are. Then there was lack of an affordable and sustainable source of cooking energy. The predominant source of energy was firewood. And the third was lack of adequate supply of clean water. So we found a school, or one of many schools run by KCCA, and we found that they had solved the problem that we were trying to solve. So we were not going to reinvent the wheel. And so we collaborated with the people who had built and serviced these biogas systems, and we learned from them, and they learned from us. And today it's taking us through that journey where we started, and this was these are photos that I share of those schools. This one is in Tanzania, and the solutions they were using, they were also using a fixed dome biogas system. For those of you who do not know what a fixed dome is, it's there are a number of different types of biogas digesters, but the fixed dome is the most reliable, which is built from brick, and gives you a stable amount of pressure as opposed to the other various types. You have also flexible liners, and all that stuff. We found that this was the most reliable. Along the way, you'll notice that I always say generation 1 or generation 2. And that's because through the 8 years doing this, we improved, adjusted, modified, and that always gives you an indication of where we are at the stage of modification. Whether it's still at generation 1, generation 2, or generation 3, which is the most up to date. Now, what was intriguing is at the schools was the ownership. First of all, at the KCCA schools, the head teachers were fully converted on the biogas idea, and extracted a small text from one of the head teachers who confirms that since the introduction of biogas, their consumption of trucks per term of firewood had reduced from 3 to 1.5 every term, which of course then solves or looks at complementing our energy needs, where we were entirely relying on firewood initially. So to understand the biogas system, this is a very basic schematic showing you the inputs, which is normally dung, and in this case, both dung and human waste. And the chemical process looks at extracting that resource, and in that process, you can convert that to gas, which you can use for cooking or lighting. The outcome is both gas and slurry, which is for fertilizer, which is very good for plants when the cycle continues. Again. So at the very top, I have what I have written: water, energy, waste. Those are the 3 components we are dealing with, but on waste, I've left a question mark. And the reason being that if you look at the cycle and the definition of waste, you could say that by recovering that resource, maybe in this case, the waste, human waste is not the appropriate word for that time. Moving on, we then show you one of the first schools and how our design evolved, both in terms of in the plan layout, in relation to the kitchen. You already see that we have our kitchen is related to the location of the biogas digester. We also have the toilets, both the female and male toilets, right next to the biodigester. And that, I would say, is a direct consequence of what we had found at many of these schools initially. And also, we were not confident with the technology we were working. And in many cases, one of many things can fail for certain systems. It could be the installation, it could be the maintenance, or it could be the users. So
where was I? I was talking about how the toilets and in this case, what you see here is a male block, a female block, and the relation with the incinerator and the biogas digester. At this time, we had the digester system, which is generation 1 down here, was not centralized. If I take you to the next slide, in the plan layout kind of shows you the relation in this case with the two yes. This is the two toilet blocks, the male toilet, the female toilet, the washing area in that case, and the biodigester, and as well as the kitchen. So the digester needs to be at least a maximum of 80 to 100 meters from the kitchen. And so there is always that relation that we followed through. In this image also, we show you the flushing tank, which we were which is fed with clean water, and that flushing tank pushes the effluent into the center, and then it goes to the biodigester in the center. So once we understood how the system worked, and also the client got confident that this is something that they could maintain. This is something that was resilient. And in resilient, I mean, where you have no water on site, is this something that will become a health hazard? And over the years, with that confidence, and that confidence also comes with support from the providers, as in they are willing to provide support for these systems. And in this case, we both become confident and are willing to explore further. And what this shows you is we then transition to a centralized system where, if I show you on the plan, we have these toilets all connected to one biodigester further downfield. And that was a huge transition, which frees up the architect and doesn't have to always have these set up the setup was originally very rigid, and it did not give him the freedom to on placement of these systems. But still, the relation is always consistent. You still have that digester in relation to the kitchen, not so far away, but in this case, we pushed it further. This was 60 meters. This is still, now in this case, it's generation 2. Why we call it generation 2, we've now transitioned, and we have, it's a centralized system. We can feed many toilets into the digester. Now, this photo shows you an improvement where we had the initial flushing tank, and in this case, this was reliant on clean water, and the photo below shows you fill this tank with water and pull this plug and flush. This is done 2 to 3 times a day, and the reason they do that is you do not want to have a lot more water than would be adequate to generate gas. There needs to be a certain balance of water and solids. The transition then from that design was this, which we first implemented at school in St. Emma, Mustard School, Junior School, Mustard Seed, sorry, Junior School. And in this case, we integrated the washing area with the flushing tank. So this was a big design change. If you notice here, we have the flushing tank at 1.5 meters above the ground. And in this case, it is only 850 millimeters above ground. So what that means is to make up for this head, we needed to dig a bit more. So you have the extra depth below ground. I'll skip this for a while and maybe come back. So still with the toilets, the transition and the learning process continued, as in what you see here was the first drop pit, and this drop pit has an integrated maggot stop. And the maggot stop is very important because when we talk about resilience, is in the event where there is no water, you should not have a system which is where maggots are coming up from the ground. And but we had problems with this one. It was not consistent. We had quality control issues, and so we then transitioned to which is generation 2, precast modular drop pit, which is the current design that we have. But that said, this also has some design flaws, and in many cases the design improvement can be internal, and a comment was made that with this one you have to be super accurate to be able to keep the items within that small circle. So yeah, but we are still using this because we are limited by what we have on the markets. The inner pipe is off the shelf, which is 160, and we would rather have a more rectangular shape, but we've not managed to have. We can't manipulate plastic at the moment. Plastic is the most ideal material to do this, and we are still limited in that regard. The other photos here show you the first manhole. The first manhole is very important in this design, and it's also very important in allowing us to freely build these systems further afield. It has a grating, and it ensures that anything that is thrown in there other than what it should is trapped. And in Chalulangera, the users found out very quickly that you need to use the right material, otherwise you will have this system blockage, and at least with constant conversation, re-education, that problem does not exist anymore, which I think was a very good thing. Still the toilet design, here we talk about the PW toilet, and our references were from the Uganda National Action on Physical Disability Design, although we modified it a bit. Ours is what you see on the right, but we were not comfortable with the outcome, and we believe this could only the feedback was not, or the change which I'm going to show you was not from the client, but it was internal. We felt that this was not adequate to cater for the varied disabilities, and we've since modified this to what we have as the generation 3 PWD toilet design, which I think then caters for a varied number of disabilities. this photo shows you what we explained earlier, that with the change in design and integration of the gray water system, as in that photo shows you how deep we have to go in order to have the head required to flush this system. Remember, this system is only flushed thrice a day, and every time you use either a volume of 40 liters. So if you're using 40 liters for a school of 500 children, you need a certain amount of pressure to push it all the way to this first manhole. The middle photo shows you the precast, the process of making the precast drop bit. Currently, again, like I said, this is the design we have. It's not perfect, and it's in, you could say, generation 2 is in the process of transition, and it's also very expensive, as you see. That pipe is the 300 diameter pipe, which is also here, and in between there is a smaller 160 diameter pipe, and that creates the maggot stop. This plan shows you a simple schematic of how the wash hand gray water recovery works. If you wash your hands there, the water ends up in the flushing tank, and thrice a day somebody comes and flushes this to this, and then there's a grating at that point, which then proceeds to the to the manholes, and then it ends up downhill. Currently, going back to the previous, currently the system has a very long name. It is communal grey water flush to biogas toilet, and any ideas on shortening this would be welcome. Now this photo shows you, it's important to show you why the system has succeeded at the outreach schools. I feel the client has been very involved, and also the support from the consultants and the service providers, and this gives a sense of ownership. Once you have a sense of ownership, I think you will take care of these systems. And this was just a snapshot of oops, this was just a snapshot of one of many pamphlets around the school that are insisting on hygiene and hand wash, and also what you need to do in order to use this system. So it's a consistent, you have to continue doing it. You don't do it once and have your hands off. I think that's part of why this has succeeded. Going back to the slide that I skipped, this is to do with the energy or the resource recovery. In cases here, they are using a simple hob, a gas hob, which we noticed is not energy efficient, as in there's so many ways that energy is lost at that point. So we came up with, through, again, collaboration, we came up with a hybrid stove. And that hybrid stove has a gas hob, and that gas hob allows, it's made of cast iron, and it allows for, in the event that there is no gas in the biogas system and biogas digester, you can still use firewood. And so this is still at generation 1. So we got it right the first time. And then in the second photo, that is the hybrid stove. This is at generation 3. And in between there, they were inbuilt, and the client, through the client, requested that we move to stainless steel and still have it hybrid system. I think this is more robust. I visited the first school we built recently. We still have the first stove built there 8 years ago, and it's still functioning. So the built-in systems also work, although they had limitations of space. The main reason why we moved to this, you're more flexible and you can move around while you're cooking your food. So lastly, I will show these slides, and this is the item that never made it to the final design for the current build that we are doing. And we were proposing to have urinals introduced, and this is something that has been done in South Africa, and we thought we could have that on a very busy day. We thought that if you had 500 or 200, if you assume of the 500, 250 girls, they would benefit from the urinal, but that never passed, and so hopefully in future this is something that can be reviewed, and that kind of gives you an insight of how we work. It's a constant push internally to improve, to iterate and generally improve the systems and the experience, the client experience or the user experience. With that, I think I beg to submit.
That's right. Thank you, Allan, for sharing your presentation. I think we will just go straight into the next presentation. And in the meantime, if anyone has questions, feel free to leave them in the box, or you can also raise your hand and we can have a discussion live at the end of this. So I'm going to hand over to David now.
Thank you, Randy, and thank you, Allan. That was a really interesting presentation, and I have lots of questions. I think that I'm looking forward to the time we get to discuss afterwards. All right, let me see if I can share here. Great. Okay, let me know if this isn't coming through. But yeah, my name is David Wituszynski. I'm really grateful to be able to share with you all today some of our work on rainwater harvesting. So just a little bit about us. Well, here's the overview. I'll talk a little bit about us, a little bit about rainwater harvesting. This research actually grew out of a case study, so I'll discuss that briefly, and then I'll share what we've done and the lessons that we've learned. So just a little bit about EMI. We are an international Christian ministry working as engineering and architecture and construction professionals. We've got offices in 11 countries now around the world. Our vision is to see people restored by God and the world restored through design. The Uganda office has been here since 2003, I believe, so coming on 19 years. Research and development is a relatively new enterprise for us. It's only in the Uganda office, and we just started 6 years ago. So we're still kind of building our repertoire of what it is that we do and looking for people to collaborate with. So certainly interested in connecting with y'all about that. Oh, and just so you know, we have a civil design guide that is available online if any of you are interested. So feel free to check that out. Rainwater harvesting is our topic today. Collection, storage, and use of rainwater. So we often have clients who ask us for this kind of system. Just to give you an overview of what that looks like, I'm sure many of you are familiar with this, but there are actually quite a number of pieces. You've got a roof that's going to collect precipitation. You're going to try and screen that out and discard the first flush, which we'll talk a lot about, store it in a tank, and then have a way of delivering it. As an organization, we don't rainwater harvesting is kind of a last resort. If in terms of reliability, it's much better to go with a borehole or with surface water, because you're never sure if you're going to get the rainwater that you expect. But there are cases where rainwater needs to be the primary source. And then even if you have a different primary source, often you can supplement it with rainwater. So sometimes we have clients who want it as a primary source, sometimes as a secondary source. That can also be valuable. We're going to be talking more about the first flush system. The way I've been describing this to people when talking about this project is rain is clean, but your roof is not. But the rain will clean your roof. So you just want to discard that first amount of water that's coming off of your roof, and then keep the water that's clean. And you want a system that does that automatically. There are manual systems where you need to go out in the rain and like move a pipe, but people don't do that. So this is kind of the standard detail from our civil design guide. It's maybe a little aspirational. We'll talk about that in a second. And there's a set volume. So in this design, you've got a T with a down pipe. That's that set volume. Our design guide says 2 liters per, or 0.2 liters per square meter. And then once that pipe fills up, the expectation is that the water then bypasses the pipe and goes to your collection system. So our case study is with one of our partner ministries called Amazima. So they're out in Jinja. They have both a primary and a secondary school. We've been working with them since 2014, and we have a really close partnership with them. This is just a view of their secondary school campus out in Ontario. And we are continuing to design and construct with them. So their primary school, which this is a picture of that, has been having issues with water supply. They have a borehole, but the groundwater keeps receding. And then national water, unfortunately, has not been reliable for them, and trucking in water is expensive. So in 2020, we installed a centralized rainwater collection system for them. And the hope is that this is kind of their primary system. When national water is on, they'll use it, but there are cases when it's off. We built a different system than we normally do. Normally, our rainwater harvesting is on a much smaller scale and a per building scale. And so that schematic that I showed earlier, where you have kind of a gutter system going to an outside above ground tank, that's what you normally do in that situation. But here we built a centralized system, and our design team really wanted all of the piping to be underground and out of sight. So what we have is kind of an individualized first flush, but then a common collection system, and then a 60,000 liter tank down here. And then that tank is pumped up to the main water storage tanks. So this is what the system looks like installed. You can't tell it's there, which is kind of the point, but you have a down pipe here, and then a first flush system here. And then kind of this alley is the collection system underground. And here's what those first flush systems look like. So it's just a box with a T going through it. The idea is that the box will fill up with water. Once it's full, the water will continue over and go enter the collection system. But we've had some challenges with this. Our client came to us and said, yeah, we're not sure if we're getting the quality of water in the tank that we want. We also didn't have an operation maintenance guide, so that's another issue. But we also realized we had never tested this kind of novel in-ground design. So we wanted to know both, is this system working at taps? And also, what can we recommend for future rainwater harvesting projects? So the research and development team was like, hey, this is what we do. Let's see what we can find out. So just to go back to our system, our rainwater harvesting system, we're focusing here on the first flush. So there are a lot of other questions you could ask about the system. We're only asking questions about first flush. And then actually there are a lot of research questions you could ask about the first flush system. The volume, another question is, are you actually capturing the water? We noticed in some of our field observations, you could maybe get water that skipped the down part of this T and just continued even when the the box wasn't full. You've got an isolation question, right? Once the box is full, how much mixing do you get between the water that you're trying to capture, which is clean, and the water in the box, which is dirty? And then you have a recharge question. So we are not addressing all of these questions. We're mostly talking about capture and isolation with a little bit of recharge at the end, just because we feel like it's especially important in these systems and something that needs more attention. So here's our experimental setup. We built this lovely box that kind of approximated the in-ground first flush system and had a bunch of ports we could put pipes into and out of and test these different configurations, and we can see into it and try and figure out what was going on. We had a tank up top to simulate water flow through the system, to give water flow, simulating rainfall. And we came up with this kind of stopper for the valve, and we could put a bolt in at a certain time and have a calibrated flow of water through the system. And we tried to use flows that were feasible for the system that we were looking at. Just to show you what a skip over test would look like. So this was us testing capture, right? How much is the water going in to the box and how much is coming out? So this is looking at the out of the pipe. So you can see that we're just putting water in and some water is being captured, some is coming out. We tested isolation by looking at mixing. So here we filled the box with a colored water that represented the dirty captured water. And then we put clean water through the system, clear water, and we measured the color of the water that came out. And one of our team members designed this clever homemade colorimeter with a cardboard box and a digital camera. And that allowed us to quantify how much color is in this sample. The idea being that samples with less color are cleaner and samples with more color have experienced more mixing. So the goal here was low mixing. Low mixing, low skip over, that's what we wanted. And then we tested a bunch of different configurations. So I'm just going to walk you through a couple of them. The first one was this single T, so just what we have installed in the field, T going into a box. We found out pretty quickly, though, that there were two ways to install this T because all the Ts we found had this sweep in them. And you could either have the sweep kind of back towards the flow of the water or the sweep forward. And that mattered quite a bit, which I'll get into. We next tried adding an extender to the T to try and reduce mixing. The idea is that it would only mix within that extender and not with the box as a whole. We tried a double T, thinking, hey, water that skips the first T might be caught by the second T. We tried this T to elbow up configuration, thinking, no way the water is going to skip over this, right? It needs to like literally fight gravity to get up there. And then also this elbow to T down, also trying to reduce skip over, but maybe with a better mixing profile than the other one. So just to throw some data at you, I'm going to walk through this, so don't be too frightened. But here are those different configurations and the kind of skip over we were getting there. And the most important thing from this graph is you look at the blue and the green. Those are the two different sweep directions for the T. So you can see if the sweep is forward, you're getting a ton more skip over than if the sweep is back. So just to illustrate that with a video, these are same flow rates, start at the same time. So sweep forward is on top, sweep back is on the bottom. Just look at the amount of water leaving and look at the amount of water in the box. You can see that sweep back is highly preferable in this system. So that's a really easy change that you can make when you're installing your system, like put the sweep in the right direction. That might have a big impact on your water quality. Other things to note, this double T reduced the skip over some, mostly at higher flows. And we didn't have a lot of skip over in either of these kind of elbow T configurations, which is what we expected. That's why we came up with them. So the lessons learned here are that your flow velocity matters, actually. If we just go back here, you'll notice that we're getting low skip over at low velocities. And then as the velocity increases, you get more. That's expected, but it's good to see that in the numbers. And then the skip over direction was heavily influenced by that T sweep. So mixing. Mixing is much more complicated to represent. We took a variety of samples at different points in the kind of flow event. This is data after 30 seconds of flow. So we expect it to be kind of the steady state mixing. You'll notice that our elbow to T configurations didn't do great. And that the extender actually makes a difference. So here's the T by itself. Here's the T with an extender, especially at low flows. That extender is helping you. So here's just an example. In this, to show this, we put clear water in the box and put colored water, promise it's colored water, into the pipe. So you'll notice that without the extender, you're getting a lot of mixing. That the clean water is infiltrating into the box, but with the extender, you're getting very little. And you do see it. You do see some of it after a while, but much smaller amount of mixing going on here. Yes, another thing to note is that these ones performed fairly poorly. You just see. Oh, yeah. So you might look at these and say, oh, look, this T to elbow up is actually doing pretty good. And given that it had low skip over, why don't we go with that? However, this was only during flow. After the flow ended, we sometimes saw like a large quantity of dirty water start exiting the box. And that was because the water level in the box actually rose during some of these tests, a phenomenon we're calling surging. And that would then kind of lower and expel dirty water during these tests. And that was particularly bad for kind of these elbow to T configurations. So just an example of that, you can see the water line rising over the course of this test. And when the test stops, all that water is going to exit the box and just kind of push dirty water out. So those elbow to T's actually weren't doing so great in this. However, we didn't have this idea, but we decided to test the idea of putting kind of a float on the bottom to plug the system when the box was full, with the idea that this would reduce mixing, especially in those cases when you're getting the surging behavior. So we tried that on both this elbow to T down and just a regular T to see what would happen. And it made a big difference. So you can see that with that, even with this pretty bad mixing profile for this one configuration, you're getting almost no mixing with the addition of that float. Just to illustrate what that looks like. Also notice the level of the water in these ones. You'll notice the one without the ball is rising a lot faster than the one with it, or a lot higher. Obviously, this isn't a perfect seal. And also, this is adding a moving part to your system. So you're going to have additional operation and maintenance if you use this option. But in some cases, we think it might be a valuable thing to do. So just some lessons learned from mixing. First, I want to point out that skip over and mixing are in competition, right? If you have a system that does very well at skip over, chances are it's going to do less well at mixing, right? Kind of the best option would just be to have nothing, just have a box in there. You'll have no skip over, but you'll have perfect mixing. And vice versa. If you're good at keeping the water from mixing, it's more likely to skip over. The T extender, though, did a good job of reducing mixing. And that, kind of the elbow to T setup, we kind of latched onto that as it's almost eliminating skip over. And if you put a ball float on it, it's doing a really good job of mixing as well. So just to end with some practical recommendations, and I've broken this into traditional above ground systems, which are most of what you see, but then also these in-ground systems because they were of special interest. So first, pay attention to T orientation. Just to remind you, sweep back is good, sweep forward is bad. And just on skip over alone, we think that justifies not using the sweep forward at all. Consider adding a second T at high flows or using this elbow to T system. And just so you know what that looks like, here's an example at one of our projects where it just happened that they put in an elbow to T. So that's what that looks like above ground. Now that's probably not doing very well on mixing, but if you have an oversized pipe, it's maybe only mixing with relatively clean water, or there might be a way to incorporate a float in there. And then, yeah, then oversize that pipe or add a float to reduce mixing. In-ground systems, that T with the extender did pretty well for low flow systems. If you have a high flow system, maybe consider that elbow to T with a ball float. So yeah, I just want to point out that our design spec actually has a ball in that pipe. We're not sure that we've ever installed a system that actually included a ball, but it is in there. So people have thought of this, and there's some practical concerns about how would this actually be implemented above ground, which is maybe something we could look at in the future. So you could see like sticks and leaves kind of jamming up that system. Yeah, don't forget operation and maintenance also. That's an important part of any system. Finally, I wanted to just mention infiltration rate. You put the water into the box, and then it depends on the soil how quickly that water is going to go away. So if you have a very sandy soil, you might actually be losing a lot of water during your rain event. So you're actually capturing much more water than you expect to. And then if you have a very impermeable soil, you might be worried that the water is staying there much longer than you want. And it rains today, you get a bunch of water in there, it rains tomorrow, and now you've got mixing with day old water. In our system, it seems like the soil is fairly permeable. So we've been trying to think about how do we constrain that infiltration rate. Maybe some kind of impermeable liner or semi-permeable liner, maybe sand. But that's something that I just want to point out is important if you're designing an in-ground system, and something that we're trying to address. Yeah, so that's all I've got. And I think we're taking questions together, but happy to answer them. This is just pointing out emails. This is my email down here. If you have questions about the Rainwater system, I'm happy to take those. If you have questions about EMI or research and development at EMI, this is my supervisor's email. So I'm sure he'd be happy to hear from you. And that's what I've got. Thank you.
Thank you, David. Really interesting presentation. And it's nice to hear different, two completely different topics, but both about water. And now we have a time when people can ask questions. So I think generally, if anyone has a question that they would like to ask, you can raise your hand, and then I will allow you to talk, and you can do that. Or you can use the box, but either way, it's nice to have a discussion, so you're welcome to ask them yourselves. I think, and both to Allan or David in any order. So I'm unmuting David Kayondo, so you're welcome to ask your question.
Hi, thank you. Don't know if everyone can hear me. Can you guys hear me?
Yes, we can hear you.
Okay.
Yes, I can.
Excellent. So my question is I actually got two questions. So first of all, thank you for putting this together. And the reason I joined this call was because Localworks has done some work for us, and I really appreciate the stuff you guys are doing in Uganda. They did a master plan for a school that we're putting together in Gaba called Aspen Junior School, and this topic is actually really close to our heart because we are trying to create a really sustainable school just for the kids as well. So my first question was around the toilets, and the system that was talked about is exactly what we're trying to think about. How do we use what we think is waste, or what people call human waste, which is mainly nitrous and carbon and hydrogen and oxygen, which then can produce methane, to effectively supplement our energy needs for cooking. So the question I had was this issue around how far the biodigesters can be from the kitchen, the farthest they can be, because in the setup we currently have, it's a master plan that Localworks put together, the toilets are downhill. And so when I say downhill, I mean elevation. Yeah, so they're downhill, and you've got the kitchen. I don't know what the distance is, but I know it's over 100 meters. And so what drives that maximum distance? Is it pressure of the gas rising up? Does there need to be some sort of, is there elevation considered? What are the key constraints to make sure that we can push the envelope? What's the maximum distance? And does elevation play a part? So that was my first question. And then the only question on the water, which you're also trying to implement around water harvesting, is the concept to try to use the elevation of the water tank to drive pressures down. And so someone is talking about underground water. But what I wanted to find out is on the T designs and cleaning water out. I know David talked about the forward thing being the sort of best recommendation in terms of cleaning water out. Is there any appendage we can add to that to make sure we get the best result in terms of quality, whether this is basic filters or anything like that? So those are the two questions.
Thank you, David. And yeah, I'll answer your question regarding distance. The reason we've stuck with the fixed dome and haven't changed it is a fixed dome biogas digester system gives you a consistent pressure. That is if all the feedstock and you're doing everything right prior to getting the right feedstock into the digester. However, distance, as you know, with even water, the further you go, you are overcoming resistance within the pipe. And the ideal distance would be between 60 to 80. But beyond that, there are mechanical ways that you can add to push that pressure further, although we are always avoiding that because of the risk of failure. So even at 100, you can still have that gas, but that's the range. We would rather between 60 and 80, and there you're getting optimum. But further afield, the pressure starts dropping. You're still getting the gas, but the pressure is dropping.
Yeah, that's what I thought. And obviously, I like the fact that in all your considerations, I've got an engineering background. You want to minimize mechanical interventions, whether it's in the working parts, because that just includes maintenance and okay, good. All right, understood. Thank you.
Yeah, and I'll answer the rainwater question. Thank you. And I'm going to say something very similar. So you certainly could add a filter or some other treatment device, but our intention was to try and minimize that. Right, a filter will require maintenance. Some other device might require inputs. The first flush is kind of a first stab at treatment where you're trying to treat the water by removing the poor quality water. So kind of what you do with the water after that, you have all the options you would otherwise. So I know that Amazima is treating water for drinking, but not for other purposes. Kind of depends on what quality of water you need.
So David, this is another question to you. I'm sorry I did ask you as a start, because in one of the presentations you made, you showed you had the main 60,000 liter tank, which is a good size, was downfield. So water coming from up and flowing down to the tank after being, going through that various treatment, and then having to be pumped up back again. So that's energy, right? So you need energy to do that, whether that's diesel, a solar powered pump or whatever. Is that a sustainable design? Because that is something we're grappling with. In other words, we want to capture as much rainwater as possible, because in a school, there's a lot of rain in Uganda. It's a tropical country. So we want to capture as much water as possible, but to do that, we need to create a significant storage that for that sort of structure would need to be underground. But then once that collects, then you're thinking about the energy to take it up to where it needs to then flow down to the various places that it's needed.
Yeah, that is a great question. I unfortunately can't speak to that design decision. I assume that they took that into account. Okay. But yeah, I would say probably the ability to capture that water is what motivated the placement of that tank at the bottom of the hill. And they seem to be reasonably confident that they have the energy to push it back up.
Cool. All right. Thank you.
Okay, thank you for your questions, David. I think maybe I can run through some of the questions that are already in the Q&A, and then, yeah, as I've said before, if anyone else wants to ask their question, feel free to raise your hand. So Jeff Wing asked earlier during Alan's presentation if only human waste and water are used, or if there's any other materials that are added to the system. So I think maybe Alan, you could answer that question, if that's okay.
Yes, thank you. Thank you for that question. No, it's not only human waste. First of all, in order to get the biodigesters going, the whole system, we have to fill it up with dung, and that gives it, it's a process called inoculation, and that kickstarts it. Then we start feeding it, during the term, it's being fed with human waste as well. And it's always advisable to supplement the waste as often as possible. And to give an example of clear numbers, the saving that was done by KCCA, the school, on when they dropped the expenditure on a truck, the 3 trucks of firewood. The alternative was dung that they were buying to supplement the biogas digester. So it requires you to supplement because the human waste is not, first of all, the quality of food. I think that's the argument, is not one that will be able to produce enough gas for you to cook. And of course, bear in mind that initially the first reason for the system is not for gas. The first reason is sanitation, and gas and the slurry is a byproduct of this process.
Thank you, Alan. Sanyu, if you would like to ask your question, you can go ahead.
Sorry. Thank you very much. My name is Sanyu Nachiganda. And thank you very much for your presentations, both Alan and David. My questions, there's 2 for Alan. One, I noticed that the flashing for the in one of the, I think in option 3 or something like that, you'd started to use the sinks as the source of water, the sinks where they wash their hands. And I don't know whether the use of soap does not affect the use of the does not affect the bacteria that is supposed to go into, that's supposed to be right in the biodigester. So I please throw more light on that. And then the other one, I was curious why, when you thought of urinals, you looked at them on the ladies' side. The norm has been that you have urinals on the gents' side, and probably, at least to my understanding, it's because when they're strictly doing the number 1, they're not likely to mix with number 2s. Yet on the ladies' side, you're doing your number 1, number 2 comes along, you just go ahead. So please throw more light on that as well.
Thank you, Sanyu, for the question. I'll start with the first one. The use of soap. We've noticed that in many of the schools, to be honest, they are not using soap at hand washing, and it's not something we designed for. It's not something we insist on, but it's something we've noticed over the years, and even then, that amount of soap is not would not be to a volume that would disturb the system. And of course, if we had if you had in one of our instructions while cleaning this toilet, you're not supposed to use soap or detergents, and there are some bio-friendly detergents that are meant for cleaning these systems. To your question on the urinal, let me go to that page. First of all, it didn't make it to the design, to the build. So obviously the other people also had reservations about it. But while you're, if you look on the upper side, the male side still has a urinal, and we were introducing the urinal on the female side. We've noticed that in the first school we built designed for 500 children. Luckily, while we were sizing the biodigester, we made an allowance, and this could take in over 800 children. And we envisaged that while much as this design took those considerations of 500 children, this could grow. And indeed, it has grown to over 700 in some of the schools. And while you have that waiting line, I think I was coming up with a way of not necessarily making the building more expensive, but allow for that person who doesn't need to go to number 2, as you've called it. I don't know if I've answered your question correctly.
Yes, thank you. I will go with that for now.
Okay, thank you, Sanu. Thank you for your question. I think, Felix, if you'd like to ask your question, you could also do that.
Yeah, thank you. I hope you can hear me.
Yep, we can hear you.
Great. My question is to David in regarding to the first flush system. And first of all, I was actually amazed by the idea to do a first flush underground. I had never thought of that, and it's such a good idea because architecturally, and of course I'm an architect, so I'm thinking about that. The overground first flush systems are really very difficult to deal with. So I of course I understand where the idea came from. I've sort of 2 questions. One is, how do you size the size of that underground first flush tank that you've done? While you were talking, I kept thinking, where does this water actually go? And then later you answered that you're sort of trying to make it percolate into the ground. And I was wondering whether there's any other way of sort of, or is there not need for an overflow or something like that, just in case there's heavy rain and persistently. Maybe you can talk a little bit more about that. And then the second question I have, we have worked with a gentleman who does underground water tanks in a very low-tech kind of way. And his recommendation is actually not to do a first flush in the first place, but instead just to place the pump, or let's say the intake of the pump that then pumps it up to a gravity tank higher up from the ground of that main collection tank, and then just basically allow any debris and any particles, dust particles, etc., to settle in that tank. And then, let's say in the dry season, when the tank finally empties, then literally just to clean it out. I wonder what sort of thoughts you have on that proposal. Thank you.
Yeah, thank you. Those are good questions. Yeah, and said the design team wanted it underground. It was the architects, and the buildings are beautiful, so they're right. Yeah, so sizing. So our design guide has a rule of thumb for sizing. I've done some literature research and I've kind of decided that it's much too small. The literature usually suggests you take the first millimeter of rain, which is 1 liter per square meter. Really, it depends on how dirty your roof gets. So if your roof is under a tree, it will probably get more dirty. If it's not, it will get less dirty. It's really hard to design carefully for that. So the first millimeter of rain seems like a pretty good solution. So those boxes should really be about 5 times the size that they are. In terms of, reusing that water. If you have an above ground system, you can use that for irrigation or some other use. In ground, it's kind of hard to see how you would do that unless you plumbed them on a slope, which we have. You could plumb them out and try and get at that water. So infiltration seems like a decent attempt. It's again, depending on your soil, that may or may not pose a problem that you need to deal with. In terms of overflow, kind of the point is that they're going to overflow, right? The overflow is the clean water going through the pipes. So you do need to size your pipes appropriately. So you need to look at available rainfall data and ask, what is my largest expected storm where I'm going to want to be able to carry that flow through these pipes down to the tank. And probably my guess is that if you have a larger storm, you're going to overflow at the gutters before you overflow inside the first flush. So that's a gutter sizing question. Although if someone else knows more about that, please feel free to jump in and correct me. As far as the tank, we actually do have that design in our tank. It's designed to settle. There's kind of a lip with the pump below that. So you're actually pulling lower, but the lip is preventing that sediment from coming in. So our concern is that you still have this, it really depends on how often you pump, right? Our concern is that you might have kind of sludge that goes anaerobic and that releases some at least odorous things into the water that aren't going to settle, and then you're going to pull that through in your pump. And really we could do some research and ask, how much is that going to happen? How much is the first flush really necessary? But the kind of the motivation for this whole project is that the ministry came to us and said, hey, the water in our tank is pretty dirty. It doesn't seem like the system's performing well. So there's also kind of this perception that this is my water, that it shouldn't be dirty. It might be hard to get over that. Even if you tell them, no, the water in the tank's supposed to be dirty, it's the water that pumps is clean. So that's a fair point. I would like to talk more about that. And
I mean, just as a simple follow-up question, would it not be just a matter of testing the water in the gravity tank, and basically because that's what it essentially gets pumped up, and that's what they're using. If you test the water in the gravity tank, you can show them whether the water is clean or not.
Yep, and we wrote an operation and maintenance plan that has them doing that, although I'm not sure it's been implemented. So that's kind of what I hope our next steps here is to see how that water actually is, and if an intervention will make it better.
Okay, thank you.
Yeah, thank you.
Okay, let me look to see if there are other questions. So David, someone is asking about the effectiveness of the floating ball. I think you hinted at this during your presentation. But maybe essentially the question is there a possibility of it getting stuck and not holding or letting any more debris into the box? So, yeah.
Yeah, there certainly is that possibility. And that's kind of the cost of the floating ball, is that something happens to it that renders it ineffective. We were trying to design kind of this open cage. I can try and show it. Can I? I can. Great. Oh, interesting. Give me just a second here. Find it and then I'll share it. There it is. So we tried to design kind of this open cage here so that debris had a chance to go through before the ball closed. But certainly once it closes, you won't be able to get debris caught by the system. So you want to design this so that it's going to close at the time when your first flush is done. Hopefully large debris is really coming off in that first wash, and But yeah, that's another thing to think about when you're designing it. This was really just our first stab at it. So I think you could spend some more time designing this and asking what's really the best solution for my system.
Thank you. There's another question from Todd. There you go. You can ask your question, I think. Hello? Hello? Todd, do you have a question? No. Maybe I can't hear him. Maybe we'll let that one go for now. I think that seems to be many of our questions. I have a question myself about operation. I think operation and like management of the system post-use seems to be quite important, both in Allan's discussion, in Allan's presentation, and in David's as well. So my question is a bit about how do you follow up with the client after you have installed the systems? Is there kind of a process that where you can watch and see what has happened? And then more for Allan, if I think you'd mentioned that twice you'd have to flush the system every day. If the client doesn't do that and maybe has not been doing it for a while, is there a way to clean out the system or to help with the maintenance? But yeah, so my question is just around operation and management generally for both of you.
Thank you, Randy. You can hear me?
Yeah.
For the system, again, I'll start with what we found with the KCCA. You find that once they buy in, the owner or the user buys in, they will look after the system and will make sure that they adhere to the processes. And like I said, if he then realizes that it's going to save him the 1.5 trucks of firewood, he then does everything else before that to ensure that the output we will guarantee the gas supplements his energy needs. But that's with KCCA. So for the other schools, let's say Cotton On Foundation, it's the partnership, and we always have the lessons learned. We go back and engage the client, and the client is always willing to share their experiences with the systems we've designed and gives feedback. And recently there was a review on the biogas systems, although I haven't gotten the outcome of that, but clearly from the fact that we're building more, that's a positive sign. And one of the outcomes, of course, was why don't we change the gas stove to something that is more movable, more robust from what we had initially. So you can see that once they own it, and with some of the images I showed you, they are involved in. You can't just build and leave these systems. The supplier is also encouraged to have these sensitization drives, because head teachers change. So every time there's a new head teacher, he needs to be sensitized and understand how the system runs and how he will benefit from a properly functioning system. I don't know if that answers your question fully.
Yeah, I think so. Thank you.
Yeah.
Yeah, for us, that's actually been kind of a thing that we are, as an organization, are trying to improve in. For some of our partners like Amazima, we have an ongoing relationship with them. So it's very easy to have those lines of communication and to see when things aren't working. But many of our designs are completed, and then we move on, and we don't actually know how well our solutions have worked. So our global office has recently started a process of going through and connecting with our previous clients to try and understand how well our designs have held up. And we're hoping that that will teach us a lot about design, but also give us opportunities to maybe remedy things that have gone wrong. Yeah, as far as operation and maintenance, though, yeah, it's ownership, exactly what Allan said. Okay. So you need the organization to own that process and to be persistent in that.
Okay, thank you. I think I see Todd's question. I couldn't hear him earlier, but he is asking David what water treatment system you recommend for your users. Or your clients.
Yeah, that's a great question. I'm not the best person to ask, actually, but my impression is that it depends a lot on the client. So if we're working with a large organization, an established institution that has a large demand for treated water, we might recommend a centralized treatment system. But many of our partners are relatively small ministries. For those, we usually suggest point of use systems. So I'm not sure what that is in most cases. I know at Amazima, they're doing, I believe, a chemical treatment. Mm-hmm. So just a batch dosing for their drinking water.
Okay. Thank you. I think maybe that's I think that seems like a good place to end the questions. If anyone else has a last minute question, you're welcome to ask now. Otherwise, we can make a summary of this and share in the newsletter. I think someone named Francis Matovu has said he has some additional resources. If anyone else does, you're welcome to share maybe via email, and then we can add them to the newsletter wherever they're relevant. Yeah, I think that's the intention and the purpose of this forum, that we continue to share resources and information as we all want to build better systems. So yeah, so if your questions haven't been answered, I think most of them are touched on, then we'll definitely get back to you. But yeah, thank you everyone for joining this session of Local Talks. And as I had mentioned in the beginning, it will be recorded. It's being recorded, so it will be uploaded to our YouTube channel and you can watch it back. And we would also like to share the presentations, PDFs, with the viewers as well. Thank you to Allan and David for your time and for preparing presentations and sharing your knowledge with us. We appreciate your time, and I guess Local Talk continues to operate through different speakers coming forward and presenting. So we are grateful. I think that's everything from me, and we hope to see you at the next event, which will be in December. So 3rd Wednesday of December at the same time, and we'll share about the next topic as soon as we are able and have more information. But yeah, thank you everyone. I don't know if Allan or David, if you have any more closing remarks or things you'd like to share, please do let us know.
No, I'll just thanking you for organizing, and thank you, David, for the presentation, and everyone who took part.
Cool.
Yeah, thanks so much for putting this together. I'm really honored to be able to speak here. Big fan of Local Talks, so I'm looking forward to the one in December.
Great. Okay. Thank you. Good night.
Thank you. Thank you.
Bye-bye.
Take care.
Thank you.